is exactly what I would hope the name implies. You're starting with a function, a formula that is the derivative of something, and you're trying to work backwards to see where you started, basically. Although backwards is relative because we think of it as backwards because we learn derivatives first. But anyway, questions about what the word means. It does use the integral symbol. The integral symbol indicates to find an antiderivative when there are no limits on the integral. So it's still the big, long S, but if there's no numbers attached to it, you don't think of it as adding anything up. The meaning changes. The meaning of the symbol is to work backwards and find the formula that we started with before we found a derivative. Question. Okay, so don't do as in the past. When I give you a handout like this, don't do the problems here. Some of them actually there is room to do it, but some there's not even close to as the space you'll need. So use your notebook. This will become a homework assignment, so you do want to have a good record of it. So when I read number 1, it's asking me to find the antiderivative of 5 cosine x. Antiderivatives, like derivatives, have a few common rules. For example, the multiplying constant rule applies to antiderivatives just like it did to derivatives. So the first thing you want to do is not pay really any attention to the 5. 5 just, some teachers say, tags along. So you write equal, pull out the 5. You still have the antiderivative of the cosine of x. Questions so far? Please, Rick.
Are we supposed to memorize this with the other one?
Yes. Yeah, you'll have to have these memorized. As always on the AP test, they don't allow any note cards or anything. So. Okay, one thing I want to caution you though, look up. Okay, on this card, there's a column on the left and column on the right. Memorize the 5 formulas on the left. Don't memorize the 5 on the right, because there's a little trick I'll show you in a bit, which will mean that you don't really have to memorize these. If you memorize the short versions of the formulas, the expanded versions are really easy. I'll explain that later. So don't memorize those 5, just the first 5. So it's a lot easier than the derivative rule sheet where we had, 16 formulas or something. So only 5. Another thing to note is on the derivative rule sheet, the formulas are different. Instead of saying cosine of x on the derivative rule sheet, it would have said something like this: the derivative of the cosine of g of x, indicating that the argument inside of the cosine function really could have been any function. The antiderivative rules are much more specific. The rule is only for cosine x, or like cosine z. It's not, it can't be the cosine of who knows what. Like if I run into this situation, I cannot use this rule. Whereas if I were taking a derivative, I could use the derivative rule, because the derivative rule allowed for much more complex arguments within the cosine function. The antiderivative rule does not.
Wait, is that where the expanded cosine rule would come in?
So 2 points for Zarin. The expanded rule still doesn't quite work, because the expanded cosine rule is going to look like this. It's the cosine of a constant multiplied by x plus another constant. So in this case, that still doesn't fit because that's x squared. So the rules are very specific when it comes to antiderivatives. It has to be a perfect match. There's not any flexibility like there was with derivative rules. I don't have a good answer for why. It's just the nature of the math, to be honest. So, questions? Please, Eric.
Couldn't g of x represent x squared plus 1, so you can just set it to like a f of x or g of x, like inside of cosine?
It's absolutely true that you could think of this as being g of x. The trouble is, I don't have a rule that allows for something like g of x. I only have a rule that allows for just x itself. That's where I get stuck. So I can't apply this rule to this situation. The rule simply doesn't fit. Does that make sense? Okay, cool. However, in this case, once I pulled out the 5, this is a perfect match for this. So just like with derivatives, all we're doing is we're just using the equal sign and declaring that this can be replaced with this. So that's what we do. I'll explain the plus c in a second. That's kind of a separate idea. So the rule is basically this is equivalent to this. Plus there could have been an extra plus 10, plus -3, something like that. So the c I'm putting on the end is simply representing the fact that if I had started with a formula that looked like this, if I were to take the derivative of this formula, so I take d of 5 sine of x plus 8, the derivative of the sine function, the 5 is just a multiplying constant, the derivative of the sine function is the cosine function. The plus 8 wouldn't have made any difference because when I take the derivative of the plus 8, I would have gotten 0. So when you're working backwards and finding an antiderivative, you have to keep track of the fact that there could have been a plus something. Plus might have been just 0, but you don't know because you're working backwards. So when we write plus c, it's simply an indication of, hey, there could have been some constant. The constant might have been 0, it might have been -3. We don't know. We just write the plus c to make sure we don't forget. Questions? You have to write the c simply as an indication that you're acknowledging to the grader that you don't know if there was a number or not. On a multiple choice test for the AP, every single answer will have plus c. So they're not really trying to fool you or anything. It's just a reminder that, yeah, there could have been a constant. Does that make sense? 2 points. Cool. So that's the first example. We're going to do several off of this sheet. Let's just keep going here. So let's go to number 30. Just kind of jumping around a little bit. Okay, another rule that is identical with antiderivatives and derivatives is the add-subtract rule. So when finding the antiderivative of 4t plus 7, the first thing you should think of is, I can treat these separately. I don't have to think of them together. And so the 4 is a multiplying constant, so it just comes out. Then I would have the antiderivative of t to the first power, like so, which is going to use this power rule. The rule is very simple. You simply add 1 to the exponent and divide by the same. So because the exponent becomes 2, I'm going to divide by 2. That's the power rule for antiderivatives. Question?
So in that case, would be 2t squared?
Yeah, it'll reduce because the 4 can divide with the 2. And you end up with 2c squared. And as a quick mental check, you don't have to always do this, but you could say, oh, if I were to take the derivative of 2t squared, using my derivative rules, sure enough, I get 4t, which is exactly what I started with. which is good confirmation that I have found the correct antiderivative right here. This is the correct antiderivative of 4t. Please, Jeff.
Why did you use the power rule when there's just not a power first?
Why there's not a power, is that what you said? So there actually is a power. We just don't write it. Like when we write t, it really means t to the first power. So the n in this case is simply 1. So it doesn't look like a fit, but it actually is. Does that make sense? 2 points. Please, Daniel.
So it doesn't matter if the 7 or the constant, if it's anywhere in there, if it's in parentheses or outside, it still doesn't matter.
You're referring to the plus c here?
The plus 7.
Oh, the plus 7. I haven't simply done that yet.
Okay.
So my first thought was, okay, I'm going to use the add-subtract rule, which means I can treat these separately. And I went ahead and just focused on the 4t first. Now I'm going to focus on the 7. You can use the power rule because it's actually t to the 0. To me, it's faster just to think for a second, go, wait a minute. If I took a derivative of something and the result was 7, I must have started with 7t, because the derivative of 7t is 7. Questions? And then I have to, oh yeah, please, Carl.
Where did C go?
Say again.
C, like C, the letter C. that
This
comes
one here?
in. Yeah, how is that going to go in?
So where that's going to factor in is, remember, the main part of the rule is right here. This really is the rule. This is just an acknowledgement that we maybe had a plus, I don't know, 11 or something in addition, because the idea is this would have been the formula we started with. And if we had taken the derivative of this formula, we would have used the add-subtract rule to take the derivative of each term separately. And when we take the derivative of that 11, the result would have been 0. But if it had been plus 8, the result still would have been plus 0. So it wouldn't have mattered. So we only have to worry about the plus c at the very end. You don't have to worry about it as you're going along. Does that make sense?
Yeah.
2 points.
So rule of thumb to add a plus c at the end.
That's a really good way to say it. When you're finding an antiderivative, don't worry about plus c until you've done everything else, and then just remember that, hey, I'm finding the antiderivative, so yeah, there might have been an extra plus 5 or whatever. So the plus c is just a final tack it on at the very end. You don't need to worry about doing it as you go along. Questions? So remember, the idea is, right here, if I take the derivative of this formula, I'm going to get a new formula right here. Oops, my bad. I'm going around in circles. If I take the derivative of this, I'm going to get this. Oh, no, I'm messed up. If I take the derivative of this, I get this. There we go. Sorry. Questions? No? Next thing. Okay, first thing, in fact, I'll pay points for this. Raise your hand. What's the first rule I'm thinking of as I look at that? Just think of like derivatives, because antiderivative and derivative are kind of inverse processes of each other. If you're taking the derivative, what's the first rule you would use? You should think the same way when doing an antiderivative. Logan? How many thought add subtract? 2 points, 2 for Logan. And then again, remember, I'm not going to worry about the plus c until I'm at the very end of the process. The 25, the -3, and the 4 are all multiplying constants. So just write them down, don't worry about them. Then we simply use the power rule right here. We add 1 and divide by the same. Add 1, divide by the same. Pull this out of the way a little bit. We'll worry about the C later, but question.
Why did you do the 5 plus 1 and the -2 and the -2?
Oh, only because I have trouble with negatives. Like, I don't have any trouble looking at 4 and thinking 4 plus 1 is 5, divide by the same. For whatever reason, negatives make me nervous. So I just wrote it down just to make sure. That's all. No special reason. You can do it in your head. You're better than I am. So I'm just not good at negatives. So 2 points for Allison. Anybody else? Cool. Now it's just a matter of kind of cleaning it up. 25 divides by 5. So you get negative 5x to the 5th. Minus. Negative 2 plus 1 is negative 1. So negative 3 divided by negative 1 is a positive 1. This would be x to the negative 1 power. This would be negative 2. 4 divided by negative 2 is negative 2.
Did you forget the 3? So would it be 3x to the -1?
How many noticed the error? 2 points, 3 for Edward. Thank you. Minus 2x to the negative 2. Questions? If this is the written portion of the AP test, you should stop there and simply write plus C. There's no need to go further. In fact, you should stop here if it's the written portion. That's very serious. You don't want to go further on the written section. Saves time, saves mistakes, get the same number of points. Multiple choice, it is possible that they will switch the exponents from negatives to positives. So the multiple choice answer may look like this. Make sure you don't move the 3. The 3 is not a part of the rule. Nor is the 2. Questions? Put it in there, please.
Isn't it -5?
Yeah. Can you use 5x to the 5th?
How many noticed that mistake? 2 points, 3 for Brinley. I wish I could say I make the mistakes on purpose because I'm very clever. It's like, no, I just make mistakes. So. Obviously, I'm a big believer in retakes. So. What's that?
At least you're honest about it.
Yeah, I've never been good at like I've had some teachers who'll say, and it's just different methods. They'll be like, oh yeah, you can like, I don't like tricking. I'm no good at it. As soon as I try to trick you, I feel guilty. So can't do it. So, question. Cool. Next one. Okay, once in a while you encounter a problem like number 11, where there actually isn't a rule that works. For example, don't be deceived into thinking that this rule here, the natural log rule, will work. The natural log rule doesn't fit because the rule only allows for 1 over x. The rule does not allow for 1 over x squared or x to the 4th. So don't be fooled into thinking that the ln rule works. It doesn't work. Question, please.
Also, let's say that it was 12 over x. Would that still be wrong because it says 1 over x?
Good question. So if I started with Well, let me back up. The 12's okay because I can use the multiplying constant rule to remove the 12. So I can do this. Pull out the 12. Actually, negative 12. I'm left with just 1 over x to the 4th. That still doesn't work as far as the ln rule. But if it were just 12 over x, it would work. You see the difference? 2 points, please.
So to fix the, to do the power rule or whatever, would we then just make the x to the 4th just an x to the negative 4th and bring it out?
Yep. Yeah, the ln rule doesn't fit, but as Zarin said, 2 points, if I do that little algebra rule, now the power rule does fit. So that's fairly common to have to do that step. Questions? Cool. So, using the rule, add 1, divide by the same. And you can do that step in your head. You don't have to write it out. Let's see, negative 12 divided by negative 3 is going to be positive 4. And they might switch the exponent back to the bottom. So you'd end up with 4 on the top, x cubed on the bottom, then you remember the plus c. Don't stress over the c, honestly. Like I was saying to Cambria, on a multiple choice test, every single answer will end with plus c. It's not something they're trying to trick you on. And on the written section, usually the problem doesn't stop here. It goes on to do a few more steps. And so there'll be little reminders that you've got to worry about the C. So yeah, it's always the same thing. On the very first day, there just seems to be a little bit of a, nervousness about forgetting plus C. No one has trouble with it after a couple of days. It's just normal on the first day to kind of think it's going to be something to forget, and you won't. It's not a big deal. So yeah. Points for Edward. Please, Carl.
Why can't you use negative 1 as the exponent?
Oh, gotcha.
And what do you do if it is negative 1?
Thank you for the reminder. So the power rule doesn't work if the exponent is negative 1, because when I try to use the rule, I have to add 1 and divide by the same. I end up with a divide by 0, which is undefined. So the rule simply doesn't work. If the exponent is negative 1, what you really want to do is rewrite the problem like this. And now you use the ln rule. There you go. 3 points for that felt good. Everybody give yourself 3. Okay. It was just so natural, like I didn't have to do anything. Does that answer your question, Carl?
Yeah.
Anybody else?
I'm taxing.
Is that just for the power rule? It's not for that whole left side?
Correct. Thank you for the clarification, Billy. Yeah, the little box that says n cannot equal negative 1 just for the power rule.
How about the n for the positive and negative 1?
So on the expanded rule, what Brindley is noticing is that on the expanded power rule, it not only references n not equaling negative 1, it also references n not equaling positive 1. The negative 1 is still prohibited. Like the rule won't work if n is negative 1. For the expanded power rule, if n is positive 1, the rule does work, but you don't want to use it. Let me show an example right here. This problem number 30 is a candidate for using that expanded power rule. The expanded power rule looks like this. Ax plus b to the n dx is is equivalent to 1 over a, and then ax plus b to the n plus 1 divided by n plus 1. So if n is equal to a positive 1, this is kind of like what Jack was saying, 2 more for Jack. The exponent here, although we don't write that exponent is a positive 1. But you don't want to use this rule when the n is positive 1. It makes the work much more difficult. It's better to just use the add-subtract rule like we did. So that's why the expanded rule has this little warning, don't use n for being either positive or negative 1. The negative 1 is prohibited. The positive 1 is simply not useful. Does that answer your question? 2 points. Cool. Okay. 3 is very straightforward. Simply pull out the 5. You're left with 1 over x dx. That's the ln rule. Don't forget the absolute value bars. They are required. Question? Again, the buff sheet here is not homework yet. We just have to stay a little bit on schedule, so we've got to get started on it today, even though the test is not due until Thursday. I didn't want to make the test due today. I didn't like the idea of making it due after a weekend, so I just wanted to give you a little more time. So sorry that it's a little bit of a disorder, but I hope that's actually better for you. So that's a nod, so that's good. Okay. Question? Awesome. Much of the buff sheet is completed in exactly the way I've shown you. It goes very quickly. It's just find the right rule. Sometimes you have to break it up by add, subtract. Sometimes you have to worry about, like we did here, moving things from positive exponents to negative exponents. But other than that, it goes pretty fast. But you don't need to start on it yet. The answers are on the back. 23. We actually have talked about already, but we'll just do it quick. Pull out the 5. You're left with x to the negative 1. We can't use the power rule, so we simply use the fact that x to the negative 1 is exactly the same thing as 1 over x. Now we can use the ln rule, and that's it. We're done. Eric.
On the written portion of the test, do you do just kind of get rid of the dx and the kind of some of the stuff when it's not quite the work, or would you recommend putting that in?
I think what you're asking is, if I'm wrong, just ask it again.
Yeah.
On the written portion of the test, you're free to go simply like that.
Okay.
There's no requirement to write the 2 steps in between. As I'm explaining it for the video and everything, I just want to be as complete as possible.
Yeah. Sorry for.
Oh, no. Does that make sense?
Yeah.
No, it's a perfect question, Eric. Don't hesitate to ask. Because really, in my opinion, how many steps you write, most of the time is you only need to write as many as you need to write. Like, there's no requirement to write more. Some problems, like we've been practicing those min-max problems on FRQs, they do have a certain number of required elements. But in general, this is just fine. Somebody else? Cool. Exponential rule, not very difficult. Pull out the 5. You're left with the antiderivative of e to the z, dz. The antiderivative of e to the z is just e to the z. That's it. There's nothing, exponential is not hard, so. That one, just the power rule, add, subtract rule again. So really, you can do it all in your head. You can just say 18 is a constant, x to the 5th becomes x to the 6th over 6. 10 is a constant, x to the 1st becomes x squared over 2. Do a little reduction. That's it. You can do a quick mental check if you want. If I were to take the derivative of 3x to the 6th is 18x to the 5th. That worked. The derivative of 5x squared is definitely 10x. The derivative of any constant by itself is 0. So, please, go ahead.
Yeah, can you just add the plus here to the second step?
2 points for Daniel. Written portion, I would have stopped here. Although, to be honest, on the written section, it's usually more things that have to be done, so I usually keep going because it's to my advantage. But technically speaking, if you didn't have more to do, stopping here would be the appropriate choice. Yeah. Okay, cool. Go on. Okay, we run into a roadblock here. I'm hoping it doesn't take a whole lot of explanation to point out that there is none of the 5 rules, none of the more expanded rules are going to fit this situation. And you cannot apply the rules to pieces of the function. Okay, the rule must apply to all of it because you're using equality. You're trying to find things that are truly equal. None of the rules look like that, so you can't use them. Questions on the reason why you can't use the rules? So there are actually many techniques for finding antiderivatives. For our class, we only use really one technique, which is the rule sheet. Added to that, we sometimes just do some simple algebraic manipulation. The third thing we do sometimes is we do what's known as a U substitution. Now, I believe in last year, they taught you a U substitution process. Can't spell. Is that right? Yeah, that's good. But the purpose of that U substitution was different than the one I'm going to show you, so the method's slightly different, so don't equate the two. But basically, you're always trying to find a rule. And then once in a while, you won't be able to find a rule, so you're going to have to do a U substitution. But the purpose of the U substitution is to make it so you can use a rule. So you're always finishing the problem with a rule. Question? Cool? So here I can't use a rule, so I'm going to try to do a U substitution so that I can use a rule. Now, as I said to Daniel, I do try to be very straight with all of you. Once you have practiced, everyone look at me. Once you have practiced U substitution for a while, you get in, there's a bit of a, it sounds kind of silly, but there's kind of a rhythm to it. Like there's just a feel for how to do this process, but it takes a little bit of time to get the feel. So don't freak out on the first example. The first example, every single time I go through this, usually most of the class feels like, how am I ever going to understand that? But it really doesn't take that many additional examples before people go, oh, now I see it. So it's just something to be a little bit patient with. So we're going to work on it today, but we'll work on it again. Like I said, there's no homework yet, so don't worry about that. Here's how it will work. First thing is to, of course, recognize that a rule doesn't work. Second thing is to remember that in our class, you don't have a whole lot of other options. If a rule doesn't work, U substitution is likely to be your only other method. So for our class, that helps a lot. You don't have to think of 6 different methods to choose from. It's like, hey, the rule didn't work, I'm going to try U substitution. I would write down the steps because they're a little bit hard to remember unless you have them written down. Okay, first thing to write in your notes. If I'm going to do a U, so listen to my words first before you write anything. Just listen to the idea, then write it down. If I'm trying to see if I can do a U substitution, the first thing I must check for is, do I have a function that really consists of two functions being multiplied? So the first thing you're looking for is two functions that are multiplying. If you don't have two functions that are multiplying, you can't do a U substitution. Now there are rare cases where one of the two functions can be a constant. So really that kind of implies that pretty much anything will work with U substitution. But it really helps to have that idea of, hey, when I'm doing U substitution, I must be thinking of two functions that are multiplied. So in this situation, I can rewrite that antiderivative as two functions that are multiplying. The two functions are 1 over 2x squared plus 1 multiplied by 12x over 1. So I indeed do have two functions that are being multiplied. Questions? You must start with two functions being multiplied. The next thing to add to your notes is the two functions have to be of a certain form. And these are your only choices. And both functions don't have to be of the same form, but they both have to be of one of the following 5 forms. Something to a number, e to something, 1 over something, sine or cosine of something. The pattern does match the rule sheet, except that there's more flexibility when you're thinking of a U substitution. The rule sheet says, hey, I can only find the antiderivative of cosine of x. But for a U substitution, I just have to be able to have like cosine of something. So in this example, this fits the pattern of 1 over something. This fits the pattern of something to a number, because remember the 12 is a constant. I really should have gotten that out in the beginning so I don't have to worry about it. So really what I have here is 12 multiplied by the antiderivative of 1 over something. Something in this case is 2x squared plus 1. Multiplied by simply x over 1, which would be something to a number. Questions? Please.
But doesn't that same thing say where, like, the exponent can't be more?
Oh, it's the exponent can't be negative 1.
This says plus.
Oh, right here. Hold on. Yeah, take your time for that. Typo, should have just said -1. Thank you. Well done. Yeah, that's just mistyped. Sorry about that. Yeah, n still can't be -1 because that would make this really this. So, question on that. Anybody else? Cool. Okay, next step. We have 1 over something, and we have something to a number. That word something is just, I don't know how else to say it. That's how I was taught, so that's the word I use. You have to choose one of the two somethings as your choice for U. The grammar sounds awful, but you with me? So you come, yeah, U again. I should probably teach it as a W substitution, but then it's not as fun. So anyway, so you pick U, in this case, to be one of the two somethings. So we could choose U as simply the X, Or we could choose u as the 2x squared plus 1. And Mr. Ruckty has a joke. He's much better at it than I am. He likes to look at this and say, well, I've got to pick one of the two somethings. It's got to be either this something or this something, because I've got to match these forms. You know, something to a number, 1 over something. And as he stares at it, he starts to say, he says, I can't remember his joke. He says, I'm going to butcher the joke. It's like, he looks at it and he says, I see something ugly. So you're remembering this now. Those of you who know. Yeah? Just, maybe it's not a very good joke. I thought it was funny. He's like, I see something ugly. Then he turns to the crowd and he goes, you is ugly. Yeah, that's funny. Okay, I got to work on the joke. I'm not good at it. So he likes to pick the ugly one because he likes to say you is ugly. See, it's like I told Daniel, I can't do it. I feel guilty. So anyway, moving on. Anyway. Most of the time, that's a good pick. To pick the ugly you. Oh. Okay, that's why he likes to say you is ugly, because it sticks in your head. I like this one better. This came from students a couple years ago, Mikkel Dahl. She remembered the movie The Help, and how the maid teaches the little girl, she says, you is kind, you is smart. It's a lot better than you is ugly. I like this one, sorry. It fits my personality better. So I am no good at teasing. I'm just not. Questions? Okay, you pick you, like so, write it down. You can't do this in your head, you'll mess it up, I promise. So u is 2x squared plus 1. The next step is to take the derivative of both sides of this equation with respect to x. So you always take the derivative with respect to the input variable. The derivative of 2x squared plus 1 is simply 4x. Questions? Okay, at this moment you should be doing a little mental test. The mental test is as follows. I picked one of the somethings as u. I take the derivative of my pick. The derivative of my pick must be an exact, not close, but an exact match of the other multiplying function. Other than, it can differ by a multiplying constant. So because this other multiplying function is simply x, this 4x is a perfect match. Because the only difference is this multiplying constant is 1, right here, 1. This multiplying constant is 4. So that is a confirmation that I've made the correct choice of u. Please.
Well, you put u equals 2x squared plus 1. Why didn't you do that over 1? Because isn't that what it originally was?
1 over, you mean?
Yeah, 1 over, oh, sorry. Yeah.
Is that what you meant? The process of a u substitution is to do exactly what you said, Jonathan. I first identify that one of the two multiplying functions is indeed 1 over 2x squared plus 1. But I notice that that is of the form 1 over something. So my choice for you is always just the something. Just the something. Good question. Does that answer your question?
Yeah.
3 points. Okay, I make my choice of u. You can go with the u is ugly or u is smart with your choice. I like the u is smart. It makes me feel better. Find the derivative. The derivative of your choice must match the other of the two multiplying functions. If it does not match, read the name for me.
Mitchell Hall.
Listen, if it doesn't match, it's not going to work. There's no sense proceeding. It's usually an indication that you've either made a mistake or use substitution simply doesn't work, and there's got to be another way to solve the problem. For this buff sheet, every single problem can be solved with simply a rule or a use substitution, so you won't run into that roadblock, but we'll encounter it in the future. Question? Please.
So does it matter which u you choose?
Oh, yes. So if I choose the other u, I let u equal just x. When I take the derivative of my choice now, the derivative of my choice is simply 1. That's a mismatch, because the other of the two multiplying functions isn't simply equal to a constant. That's 2 points. Yeah. Cool. Okay, now we. Oh, yeah, please.
So if they're both equally ugly, do you just choose one randomly and hope it works? And if it doesn't, then you do the other one?
Yep.
Okay.
Yeah, listen, class. Listen, hey. No, it's really true. You just do the little check. In fact, as I told you, there's a bit of a rhythm to this. I can look at, it's just experience. You'll get the same experience. I look at that and I immediately can mentally see this. And I just do quick derivative checks. I think, well, the derivative of 12x isn't that. Oh, but the derivative of this is that. So now I know what to choose as u.
Okay.
Please.
Is there ever a situation where like they won't match either when you do it?
Yes, you'll hit situations where there is not a way to use use substitution. So use substitution is not a always works method. It's a works in some cases method.
You probably already said this, but if with the case of the constant of 12, can you said that the derivative here ends up being 4x, which works for 12, right? So does it matter, or does it ever matter if we have the constant on the outside and just do 1x versus the 12x?
That's kind of personal preference, honestly.
But it won't.
Doesn't affect anything. I find it easier to take it out. I think it's easier to understand, but it's not a requirement. Nelson?
So what if there's more than 2 functions in this?
Like 3 things being multiplied,
Uh-huh.
then use substitution won't work.
Okay.
Yeah, there'll have to be another method. Point. Now, the good news for our class is the only problems they're going to give you, it's either going to be just a rule, it's going to be a use substitution, or there'll be a few other cases I'll show you, and that's all you worry about. So, not really much chance of running into something where honestly you'll get stuck. If you're not getting through it, it's usually because you just have forgotten something about use substitutions. Okay, next step. We make the substitution right here. We are going to replace 2x squared plus 1 with the letter u. So you come over here. There's 12. Antiderivative, 1 over u. And then we still have an x dx. Question?
From there, can you do the rule?
We can't use the rule yet because it's still a mismatch. Because the rule says it's got to be 1 over x dx. Or in this case, we're looking for the rule to look like this, 1 over u du. So we have to make one more substitution. We've got to replace x dx with something that is equivalent. Because look at me. I've been saying it all year long. It is all about the equal sign. It's finding something that's equal to something else. We don't think of equal as pointing to the answer. We think of equal as these 2 things are the same, we can make replacements. So we've already made one replacement here. We're going to make another replacement by noticing that if we simply multiply both sides of this blue equation by dx, you get a new equation that says du is equal to 4x dx. If we then move the 4, we get 1/4 du is exactly equivalent to x dx, we now know how to replace the x dx. The x dx can be replaced with the 1/4 du. Questions? Really, please.
You can multiply by the dx on both sides.
So your reaction, sorry, I have to celebrate my memory here. Your reaction is exactly the reaction I had in 1983. I'm a very old person. The first time I saw the teacher do that, I had the exact same, what are you doing? You can't do that. But remember that a derivative is just a division. It's just the change in this divided by the change in this. So you can undo the division.
Okay.
We just haven't used it yet, but it's not like anything really that's different than you've known all your life. Does that make sense?
Yeah.
It's well done. Okay, so anybody have trouble seeing that x dx really is exactly the same thing as 1/4 du? So because they're the same, I just make the replacement. 12, 1 over u. Oops, that's 4. 1 over u. And then x dx is 1/4 multiplied by du. Because the 1/4 is a multiplying constant, it can be moved out front. A little bit tight on space here, sorry. So you get 12 divided by 4 is 3. 1 over u du. And as I said earlier, the purpose of a u substitution is to get to where you can simply use a rule. We're there because we can now use the ln rule. Our final answer is going to be 3 natural log absolute value of u. We make one more substitution. We put back in for u its original value, 2x squared plus 1. If you were to take the derivative of this formula, the result will be this formula. Please.
All the tests to define u, do you have to actually put it back in? Or can you just leave it as u?
Good question. On the multiple choice section, they will always put it back in. On the written section, what is most common is they'll actually say, show that the following antiderivative is such and such. So they'll be giving you a reminder to put it back in. Per the rules of the test, because they're the same, you really shouldn't have to, but I'd be nervous not doing it. I think I'd want to demonstrate to the grader that I understand the process completely, so I would put it back in. Good question. Please.
Is it always going to look like x dx, or could you have like sine dx that you were trying to?
Say it again, David.
Is it always going to be x dx that you're like multiplying by? Do you know how you did that? You multiplied both sides.
Like here?
Yeah.
Oh, good
What if
question.
it doesn't look like x dx, but it's sine x dx?
It could be sine x dx. Oh, for sure. It can be all kinds of things. What you're looking for is right, like come up here again. I made my choice of u. U is 2x squared plus 1. So I know that this is going to become 1 over u. So whatever the other multiplying function is, that's what you're trying to rearrange for.
Okay.
Here it was x, so we rearranged for x dx. If the other multiplying function was sine of x, we'd rearrange for sine of x dx. Does that answer your question?
Yeah.
It's important. Awesome. That's it. That's u substitution. So we'll practice more, but I wanted to make sure we got started on it just because we always have a deadline of May 4th. So good job, Bill. We're in about a minute. So.
That's exciting.